expecting to finish it this quickly, but alhamdulillah. All right. Slideshow, set up slideshow, remove animation. Okay, and then slideshow. All right, now here is where, like, this is where the batch previously, I don't know which one, but this is where everything went wrong. I showed them these questions and like no one got anything right, and then we had to redo hypothesis testing again. So I hope all of you can answer this. Okay, let me get the chat up so I can either be disappointed or proud. You guys determine it. Thank God I pressed enable editing. So question 1. When we calculate power in the exam, you're gonna have to ask the doctor. I don't know. It's not on your slides. I'm not gonna talk about it. All right. So now question number 1. Which of the following represents the power? Okay. So why is it not A? It's because, you know, there are 2 correct decisions. So the better answer here is B. If B was not here, you know, A is the best answer here. Even though it's not perfect, it's the best answer here. But B is the best choice. So B here is the best choice, right? So yeah. So question 2, beta, blah, blah, blah. This is just simple. Type 2, right? So 3, what do we aim to do in decision making? See, he doesn't give you the decision because that's too controversial. He just tells you, what do you aim to do in decision making? What do you do? So let's go on question 3. Yeah, you want to minimize alpha. Exactly. You want to minimize alpha. So we talked a lot about this. So 4, what happens to power of a statistical test as the sample size increases? Increases, exactly. He could say, for example, if the effect size increases, if you decrease alpha, yada, 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 blah, blah, blah. If you increase alpha, sorry. If you decrease alpha, power goes down. But yeah, so this is just things that you need to think about, and you need to put all this theory in your head. Either commit it to memory or understand it. So what is the p-value obtained in a statistical test? I love the definition, so please no one like disappoint me here. C, exactly. It's the probability of getting the result or beyond that result given that the null hypothesis is true. I don't like using given, I like using assuming. So this is just wording issue. But yeah, it's fine. What is the probability of a type 1 error? Okay, so here, no. Don't answer this. We're gonna go through each option, okay? So A, probability of not accepting a true null hypothesis. What is this? What is this? Probability of accepting a true null hypothesis. Right, this is correct decision. This is correct decision. Okay, so I'm gonna put that as C. It's not power, it's the opposite one that doesn't have a name. Probability of accepting a false null hypothesis. What is this? Probability of accepting a false null hypothesis. This is alpha. This is alpha. Exactly. I'm really proud of you guys. Okay. Probability of accepting, sorry, no, there's no or not. Probability of rejecting a true null hypothesis. What is this? Yeah, look, some of you are saying correct. Listen, wait. Focus. Calm down. Probability of rejecting a true null hypothesis. Guys, relax. أول شيء. It cannot be alpha because the question is asking for alpha, and we already said that this option choice is alpha. So there can't be 2 alphas. Okay? So relax. Again, rejecting a true null hypothesis. Okay, wait. Listen. Like I do not understand what you guys are saying. This was correct decision and this was alpha. Now I am sure that all of you broke your promise and none of you drew a mind map. You're just answering from your head. And that's why I'm seeing a lot of incorrect. So I'm actually drawing the mind map in my head. It's time to actually do the mind map. Now I'm gonna answer. All of you are just gonna watch, okay? Because all of you are getting confused. C. Just 1 second. I'm gonna erase everything. And I'm gonna do them all using the mind map, okay? Okay. So here, this is the cutoff, right? This is the cutoff. A, probability. Don't type in the chat. Don't type in the chat. I think maybe I quickly follow the chat. I'll show you how you go through each option using the mind map. Probability of accepting a true null hypothesis. Okay, so the null hypothesis is true. So we're in the top part, and we didn't reject it. We accepted it. So we're here. So this is 100% a correct decision. Okay. Now B, probability of accepting a false null hypothesis. So they already told you that this is false. So we're not here. We're actually here. We're in the bottom part. Okay. So, you know, since they said accepting a false null hypothesis, we're making a mistake. So this should be beta. Are you all with me on this? This should be beta, not alpha. We previously put it as alpha because we weren't using the mind map. Do you all understand this? Let me put beta here. Rejecting a true null. Why is it not alpha? Okay, wait. Rejecting a true null. Because look, it's not saying rejecting a true null. It's saying not rejecting a true null. It's tricking you. It's doing a double negative or whatever it's called. It's saying probability of accepting a true null hypothesis. Lean, did you pay attention to this mistake? Because it's saying probability of not rejecting. It's actually, forget this entire thing. Just say accepting. Did you get it? Did you get it? Just say yes or no. Yes, okay, yeah. So it's not just rejecting the null hypothesis or the true null hypothesis. It is actually not rejecting the true null hypothesis. And that's the same as accepting the true null hypothesis, which is the correct decision. Now, can you all agree that the choice B here is beta? Because it is the chance of accepting a false null hypothesis. If it's the false null hypothesis, but we actually accepted it, that means we made a mistake, right? H1 is true, but we think that H0 is true. We accepted it. So that would be making a beta mistake. Do you all understand this? Okay. I want to prepare you guys. You guys are going to do option D. Now, I will do C. You guys do option D, okay? Just calm down. No one answer. So option C, probability of rejecting a true null hypothesis. Okay, so they already told us this is true. This is true. So we're up here. Now, did we reject this or did we accept this? Okay, so it says we rejected this thing, which is true. So we're on this side, So what's this side? It's alpha. So this side is alpha. And that's going to be our answer. That's going to be the answer. It's going to be C. This was, I think, also C. Right? Now you guys do D. Relax. Don't answer quickly. It's saying rejecting a false null hypothesis. Okay. It's saying that the null hypothesis is false. So first off, we know that we're down here. Now the question is it power or beta? Now it's saying we rejected the false null hypothesis. Well, you want to reject the false null hypothesis. You want to go to the right side, which is going to be, in this case, on the bottom side, power. So this is going to be power, right? The problem we had was using this beta, we thought it was alpha, right? So admittedly, I played along because, you know, I wasn't using the mind map. This is why you use the mind map, right? Now this all makes sense to you. Okay, now we're going to play again, but this time it's all of you, okay? This time, all of you are going to do it. So we're rejecting the null hypothesis when it's false, so we should accept, yeah. So another way to term it is we're accepting the alternate hypothesis, right? And that basically is the same as saying we're rejecting the false null hypothesis, which is the same. It's all power. So, okay, everyone, choice A for this one. What is it? Probability of accepting a true null hypothesis. Wait a minute, is this the exact same? Oh, okay, no, never mind. No, we're not doing this anymore. This is the exact same as this, so you guys can just cheat. So it's fine. So this is correct decision. This is beta. That's going to be the answer, right? Beta is the answer. And then that's going to be alpha, rejecting a true null hypothesis, rejecting this, whatever is here, and going this side when it's, you know, wait a minute. Probability, yeah, rejecting a true null hypothesis. So this is true, but you rejected it. So you made a mistake. So you're in alpha. And then, yeah, this is the exact same thing. So this will be power. Yeah, it's the exact same wording. All right, I was hoping we'd have more questions so we can keep testing this principle. But all of you sort of understand it, and you can always go back to the recording and see everything. And, you know, this will hopefully be clear as we keep going on. So, yeah, now let's do question 4. What's question 4? What's the answer? Yeah, so it's A. So it's going to be basically C, C, B, and A. Now, in question 4, how would you make the option C correct? If it's wrong, but how would you make the option C correct? Yeah, you either say population or you change this to 100%, right? There's two different ways. Either you do that or you do that. So yeah, this is the questions. I think there are more. No, there's no more. So now we enter the second lecture. It's actually not that difficult. I think this should take maybe 30 minutes and the next one 30 minutes. Look, this question is actually, this lecture is actually really simple. The problem is people want me to keep calculating everything that I'm saying. And people will keep saying, where did you get this number? Where did you get this number? This entire part of the lecture, we're no longer talking about calculation. You will see results and numbers and like this, but no one should really be asking me, how do we calculate it? I could show you, but it has no bearing on understanding the principles in this lecture, okay? So remember all that talk that we were saying in just 1 second, there's a question. Rejecting a false null hypothesis, rejecting a false null hypothesis is power, and accepting a true alternate hypothesis is, it's also power. Accepting a true alternate hypothesis is also power. It's also a correct decision, but better to say it's power. So yeah, I agree with you. Rejecting a false null hypothesis, you want to reject it when it's false. That's power. That's a correct decision. How do we differentiate? No, you don't differentiate. Like if he puts both options, those are both the correct answer. What you do is you select one of them, then appeal. Is it okay if we take 5 minutes break? Yeah, of course. If you need coffee, get coffee. We'll take a 5-minute break, and whoever needs, like whoever wants to ask a question, you can ask a question. Can I ask that question from earlier? Yes. So for the second map, both correct decision and power. Yeah, this area, it could be called correct decision or power, both. But the reason we don't say correct decision, like don't try not to pick that if you find power, because saying power is the better term here, because this is technically also a correct decision. I do not see what this, in which 5% of such intervals contain the parameter of interest. No, this is wrong. This is wrong because it should be 95. 5%, if they said does not, if they said here, right here, does not contain the parameter of interest, that will be correct. But it didn't say that. It said that 5% contains, so that's wrong. C, it says with 95% certainty of containing the sample statistic. That is wrong, because it should always be 100% that you include that sample, always 100%, and never anything below that. So yeah, that's why C in this case is wrong. The actual correct answer is A. And I put it here. So let me see the open file. I draw it, one like this, and then one like this. Line, and then there's like, this has a mean and this has a mean. But basically, this is the cutoff. Basically, to the right of this, the p-value is significant. To the left of this, the p-value was not significant. Anything to the right, it means that you accepted the alternate hypothesis. If it's to the left, you accepted the null hypothesis. This is independent of reality. So let's say here it's H0, and here it's H1. If your p-value was this way, in other words, you accepted the null hypothesis, and the null hypothesis is true, that's the correct decision. If you accepted the null hypothesis, but H1 is true, and that means that you're actually down here, right? You're at beta, because you accepted this, but this is the true part. So you made a mistake. You could reject the null hypothesis, but it's true. So you think that this is the answer, but this is what ends up being the correct thing. So that's called alpha. And sometimes you can accept the alternate hypothesis, and it actually is true, and that would be power. P to the left means it's great. Yeah, P to the left means it's greater than 5%. P to the right means that it's less than 5%. Meaning that it's, this way means significance. This way means it's not significant. So yeah, now it's time we deal with Z versus T, right? Z versus T. Remember when we were talking about all that stuff about how, oh, hey, assume that you know the population, assume that the graph is normal, assume. The reason we assumed all of that was because we had to explain biostats to you. But now we're doing the real thing. We're actually, we're going to show you samples and how people do the real thing. So for that, we don't use Z anymore because Z assumed that we knew the population mean. It assumed that, you know, we had all these assumptions that aren't true, you know, that we had to change something. So instead, we have T. So we can use T even if we don't know the population mean. That's why we like it so much. So a problem arises when we do not know what sigma is, the population standard deviation. So what we do, basically you can't use Z if you do this. Basically, I'm not going to go into why. It's going to take me like 5 million hours. But basically, if you take a sample and then find a standard deviation of that sample, you can assume that that sample's standard deviation is very similar to the population standard deviation. Once you make that assumption, you no longer use Z, because Z's assumption is that we know the population standard deviation, right? As the second you start making a sample and assuming that that is the population mean, you can no longer work with the other assumption. That's why you don't use Z. That's just the basic way of explaining it, but it's more complicated than that. So this is the T table. You don't need to know how to read it. I don't even know how to read it. But basically, it takes into account the degrees of freedom. It takes into account how good of a confidence interval you want, lots of things. And then it gives you a T value. And then, you know, these are all, you know, T values. And then from the T value, you basically get a P value. Okay. And this is really, confusing. With the Z table, all the P values were here in the middle. But no, these are all T values, right? So, yeah. I hope this so far is kind of clear. We're gonna cover more of this. Yeah, he won't bring it because, you know, no one likes to. No one reads T tables. Okay, people just put it into Excel or into Jamovi or into RStudio or into whatever, and then they get the number that they want. They don't go through the hassle of reading this, you know, table. So, yeah, this is called the student's t-test. Why? Because the student actually came up with it. So that's why they call it. You know, usually we don't know what this is, so we use the t-test. And it's much more common than the z-test because in real life we only use the z to explain to medical students how to, you know, deal with biostats, and that's the only use for z value. We don't have a use for it other than that, really. But t-test, it can be used practically. In fact, if you go into Excel sheet and write equal t-test, you'll find it, right? Because it can be used practically. Now, when you have a large sample, sometimes the value that you will get, for example, the p value you'll get with a z, is very similar to the t value and the t value the p value that you will get with the t, right? But that's only when your samples cross 100. In real life, if you're making a really big study, if you're like the WHO or something, you'll break that number very easily. You'll have thousands upon thousands in your study. But if you're just a resident in a hospital and you want to do a study, you know, if you have 30, 40 people in your study, that's more than enough. In fact, people say, you know, this is another guide that 30 is really the magic number. Now, 30 isn't the magic number in Al-Faisal. If you're doing a study in Al-Faisal, you want to get like a sample of 300 people because, you know, you can get that. But in a hospital, generally the magic number is 30, especially if the disease is very rare. Therefore, you have small samples. And he goes on to really tell you that small is beautiful, right? Small samples are really good to work with. Why? Because if you have a really rare disease, if you have Fanconi anemia, you don't want to, like, you might spread you might go through all of Saudi Arabia and just find like 20 cases. So you should be happy with those 20 cases, right? And this is all of Saudi Arabia, not even just Riyadh. Like in Riyadh, there's a I forgot the name of this. There's like a hospital, like Children Cancers Hospital, whatever. It's like linked to KFSH, but it's like an hour away. You'll be rotating there in like one week, inshallah, if like nothing like Corona happens or something. The point is, when you rotate there, you will like. I was really lucky, and my group was really lucky. We managed to see a case of Fanconi anemia. One case. And the doctor, even he said, like, you guys are very lucky. Like, usually we never have these cases, but here you go. Here's one case. And really, you get to see all the features and everything, and it's nice. Prince Sultan, maybe, maybe I don't know. But point is, um, the idea is that when a disease is very rare, it's hard to get a large sample of that disease. Same thing with the cost. It's better to have a smaller sample because there is less cost, effect with it. It's a lot cheaper to do a smaller to work with a smaller sample. You can work much faster with a smaller sample. This one makes sense. You don't have to analyze like a million people. Just, so 30, 40 people is good. You can go into greater depth. What that means is that instead of taking the height of a million people, only the height, when you have a 30 people, you can start going detail with them. You can take the age, the weight, the height, the marital status, the gender. You can take many different things, and this helps find more associations. Greater accuracy in general, this kind of feeds into depth, but generally you're able to become more accurate with more people, with less people, sorry. And the best way you can explain this is, like, let's say you want to measure blood pressure in patients. If you have like 100,000 people in your study, you're going to be happy to just have the automatic, cuff. But like everyone knows, the automatic cuff will never ever replace manual, determination of blood pressure. Now, obviously, we say this, but if someone is really good, really, really good, no, guys, forget hospitals. It's something called CCC, like something like this. Forget the hospitals. Point is, if you have like 50 patients, it's very easy to do all these 50 patients manually. But if you have 100,000 patients, you're going to use the cuff. And in general, I know everyone, people they'll assume that, oh, manual is really tough on me, I'm going to trust the cuff. It's actually the opposite way around. And I know, like, you guys, they taught you how to measure blood pressure, right? Did they? Yeah. So I'm gonna here. I'm gonna ask all of you. Did anyone actually really hear the Brewy and learn all the Korsakoff sounds? Because there's 5 Korsakoff sounds, and it is good to practice how to do blood pressure either on your. Yeah. None of you heard it, right? None of you heard it. No, only one. Even that one person. I'm sure he didn't hear. Okay, no, I'm not sure he didn't hear it. But yeah, no one really perfectly learns how to do this, and I don't blame them because the auscultation is very difficult. But I don't know. Like I think that with practice, you'll begin to understand that measuring blood pressure with manually is a lot better. And I'm not saying this to like I'm not that good yet. I hope I could be that good. But the point that I'm trying to say is that you can be more accurate with a manual cuff than an automatic cuff. And for that reason, if you have 100,000 people, you're not going to go manually through each one. Therefore, your accuracy is going to be less with 100,000 people in your study. It's going to be better with 50 people because you can do them manually. You can put more care and accuracy into measurements and so on and so forth. So yeah. So they go on to give you this example. This example is really fun. It basically says that we want to see if people will be smarter if we tape the phone to their heads and then we make it work. We turn it on. And they're like, will it make them smarter and get better grades? And they just get, this is fictional data, whatever, forget it. They're like, let me take a population of the men and then let's do a random sample, okay? And then we'll see whether people who did the SAT exam with the phone on their head, did they get higher marks than the usual population, the usual population, the SAT score, right? So now we don't know the population mean. So what we can do is we can find the mean of all of this. I think he finds it out and it becomes 6.5. And then he can find the standard deviation. So it's going to be 2, right? Standard deviation here is not of the population, it's of the sample. So if you find the variance in the standard deviation of the sample, you'll end up eventually with 2. Now this 2, we're not going to use it because when we have a sample, we don't use standard deviation. We use SEM. So now this standard deviation, the reason we found it out is because, like I mentioned earlier with the t-test, we have to assume that this sample standard deviation is the population standard deviation. Then we do SEM. So we do 2 divided by radical 16, it becomes 4. Then our final SEM is 0.5. You put all this information, into the t-test, Jamovi, whatever you want to call it. He gives you the population mean, but he should not give it to you, whatever. He gave you, you found out the standard deviation and it was estimated from the sample. We assume that it is the population, blah, 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 blah. All that stuff happened. Then we make our null hypothesis and alternate hypothesis. Our alternate hypothesis is that, this is really important, because this is really important. taping the phone on your head can make you do better or worse on your exam. Okay? Not just better, because remember, it's two-tailed. Previously in the hypothesis testing lecture and in the mind map, I just made it simple. We only considered one tail. But now we're doing the real stuff. You always consider both tails, right? It could make it better, could make it worse, right? And then the null hypothesis means that taping the phone to your head will not do any difference. So then basically we have all the data. This is our sample mean if we did not use SEM, but of course we did use SEM. So here's the SEM. This is with a standard deviation of 2, which will make it not significant. This is the wrong way of doing it. This is the correct way of doing it, with using SEM, since we use a sample. Here it is significant. And if we go here for the summary, you'll see that the p-value was less than 0.05. And more importantly, notice the confidence interval. Didn't we say that the population mean was 5? Does this confidence interval cross 5? Are you guys even with me? No, okay. Amal, you mentioned no? No, okay. So because it doesn't cross 5, that means it's not significant. That means it is significant. It is significant, right? I kind of confused some of you, I'm sorry. But basically 5.4 to 7.57. And 5 is here, right? This is the mean. That means that because this doesn't touch the mean, it's significant. This is the same concept from the confidence interval lecture. So this is significant. It agrees with the p-value, which says that this is significant. And then you make a summary. You tell them, hey, taping the phone onto your head while it's on will make you better during your exam. Right? This is how studies should go. Right? This is how studies should go using the t-test. This is just a simple example. So what kind of questions will we get from this lecture? I'll mention. You'll get questions about the small is beautiful slide. This is, I am sure, inshallah, there will be a question from this. If not, whatever. But can you repeat, please? We still, look. Repeat what? We still didn't say anything. Like, this is just the typical study. They did a study. They found out the mean. They found out the standard deviation. They found out SEM. And then they basically found out everything and put the results in front of you. And the results say that it's significant. We still did not talk about anything. Anything. We didn't talk about anything. Still, the question, look, we still have so much theory. Sorry, whoops. No, God damn it. Look at what you guys made me do. Well, I did it, but like I accidentally ended the lecture. We still did not talk about anything. I'm just showing you how they made a study, and here are the results. And the results tell us that it's significant, both the confidence interval and the p-value agree that it's significant. Let me bring up the chat. So there's nothing to repeat. It's just a study. They set up the hypotheses. They found the data. They figured out that, hey, it's significant. P-value is less than 0.05, and the confidence interval does not touch 5, meaning it's significant. So both the p-value and confidence interval always agree. They're always, they try and say the same thing. Can we please stop after this lecture? I agree. I will stop after this lecture. Then please tell them tomorrow that I'll be giving ANOVA at the beginning of the lecture. It will take me around 30 minutes to an hour. Okay, so let's finish this lecture. All right. So, yeah, there is nothing to be like. Look, all of you, please answer me this. If this is the confidence interval, and this is the mean, and this is the population mean, but you don't really get to say that. You don't need to get to say that. Is it significant or not significant? Yes, it's significant. It's significant, right? We all agree with it. We are not saying anything new. Nothing new so far. Nothing new. I'm just showing you how they do their studies, right? Okay. Whatever, this is just history. All right, now we're learning something new. There are 2 types of t-tests. There's one called a dependent t-test, another one called an independent t-test. Basically, the difference between them is this. Let's say you get 16 people and 16 people. I want everyone to look at the camera just for a bit. So 16 and 16, okay? Now, if you have this group taking drug A and this group taking drug B, you have different people taking different drugs in different groups, right? This is called an independent t-test. Independent because these people are independent of these people. They're not the same, yada, yada, yada. But what you can do sometimes is you can have the same 16 people take drug A, then take drug B, like this. Same 16 people, only like here that we have 32 people with this example, the 16 and the 16. You can just take 16 people, give them drug A, record the effects, collect the data, and then wait like a week or something until the drug washes out of their system, then give them drug B, and then collect the data. Here you'll have two different, sets of data. You'll have technically two different groups. However, they come from a dependent, group, one single dependent group. And that's why we call it dependent samples t-test. The theory in this lecture is basically what are the advantages and disadvantages of each single group. And we'll talk about that near the end of the lecture. But for now, let me show you how they do some studies, because this is kind of important, okay? He might show you this results screen and ask you questions on it. So you need to understand how to analyze this. This is more important than you asking me, how did they find this number? How do they find this number or this number? How do they find this? No, we don't need to know that. What we need to know is, how do we read this stuff? What does this stuff mean? And we'll talk about that. So here, what they did was a dependent samples t-test. They got just 16 patients. They first gave them drug A, then they waited like an hour, like a week, and then they gave them drug B. Now, they assumed that everyone sleeps 8 hours. So they marked that 8 hours as the null value. They marked that 8 hours as 0. Anytime they sleep, for example, if someone slept 1 hour more, if someone slept 9 hours, they would collect that data as 1. All right? I hope this makes sense to all of you. This is just convention. So here, for example, when patient 1 took drug A, he slept for around 0.7 hours more than 8 hours, okay? When he took drug B, he slept for around 2 hours more. Same thing with drug 2, blah, blah, blah. Okay. So then what they did was they found the mean of all of this for drug A and the mean of all of this for drug B. They found some other parameters, statistics, like for example, standard deviation, blah, 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 blah. And then they set up their hypothesis. So here he mentions it very nicely that saying, is drug A or drug B soporific? That's not enough. So this is not enough for an alternate hypothesis. Basically, your hypothesis should include whether the drug makes you more sleepy or less sleepy. So the best alternate hypothesis here is that do drugs A or B have any effect on sleep? Now, this is not really the alternate hypothesis. The alternate hypothesis says that drug A and B have an effect on sleep. Now, I need you, because I remember that it wasn't our batch. It was either 9th batch or 10th batch. They had a question like this, and they kept asking me about this. So they were telling me, we had one question. He gave us the study design, what they wanted to do, like for example, this study. And then he asked us, which of the following is the alternate hypothesis? And then he gave them statements. Some of them picked, do drugs A or B have any effect on sleep? That's not an alternate hypothesis. That is called your research question, right? That is the question you want to explore. That's not your alternate hypothesis. Your alternate hypothesis says that there is an effect. Even if there isn't, forget if there isn't or there is, it says that there is an effect. And he might flip the question, he might say, what is the null hypothesis? And it will be that the null hypothesis says that there is no effect. All right, I need you guys to understand this. Don't pick this as a hypothesis, this sentence. Yeah, he asked us, yeah, I know him, because this is an important thing, and he'll talk about it more in 3rd year for you guys, because this is important. You need to know the difference between a hypothesis and a research question. A research question is just something you want to explore. For example, does giving, for example, Kit Kat make people get better grades? That's a research question. It's not a hypothesis. A hypothesis would be Kit Kat, or the alternate hypothesis would be Kit Kat does give you better grades. And the null hypothesis would be Kit Kat does not give you better grades. But, does Kit Kat give you better or worse grades? That's not a hypothesis. That is a research question. Now, we have BEP in 3rd year. Yeah, you have EBM. Yeah, evidence-based medicine, which is more theoretical, no calculation, more theoretical. Okay. You won't need crash courses. EBM is a lot easier than MyStats. Okay, now another thing that he might ask you, this is another very clever trick, is he'll tell you which of the following is the alternate hypothesis, and he'll say, drug A and B make you sleep more. This is wrong. The best alternate hypothesis is that drug A or B make you sleep more or less. That's the alternate hypothesis. Now, because this, now a lot of you might be like coming and say, Khalid told us that this is the answer. Why is it not the answer? If in the question, I'm just making it a bit more complicated. If in the question he mentions that we're only doing a one-tail test to see whether the drug makes you sleepier, then the answer would be that the alternate hypothesis is only does the drug makes you sleep more. That's our alternate hypothesis, because he specifically mentioned that it's one tail, right? He specifically mentioned this, and that's where you need to, like, something needs to click in your mind. That's what is one tail and two tail test. Okay, so any hypothesis, you have to consider that it will go this way or this way. For example, I'll make it so stupid, but this is the correct way of saying it. Pain. I have 5 million, I have 50 cancer patients, okay? And I want to check if giving paracetamol at a dose of 2 milligrams, okay, would, decrease their pain, or decrease their pain. The alternate hypothesis here, imagine this. You actually have, the correct way to say it is that paracetamol will decrease or increase their pain. You cannot just say decrease pain, unless if in the question they mention that they only care about one tail, which is, this tail, which is the decrease the pain part. But every other time you mention two tail. Now, why is this important? This is actually, you don't need to know this, but this is more important for step. It's about bias. When you say that, for example, let's say I picked that, my alternate hypothesis is only that will paracetamol decrease, or not will, it's not a question. Paracetamol will decrease their pain. That is such a biased statement. Because how do I know? I know paracetamol decreases pain, so I just assume that that's the alternate hypothesis. That is incredibly biased, because you need to always consider the fact that paracetamol might increase it. Okay, here we go. Is it possible for paracetamol to increase pain? Is it possible for someone to be 60 feet tall? Is it possible for a Friday to be before Thursday? Yes. So that's why you always take two tail, unless it's mentioned. But even if they mention it, their study is wrong. I doubt that their study would get published in a very good place. You always take two tail, because the second you take one tail, it's like you already admitted that you're biased. You're saying that paracetamol can't increase pain. No, it can. How can you say something like that? Especially with numbers. Like, that person is saying that, oh, look, Khalid is such an idiot. He thinks that someone can be 60 feet tall. No, I am sitting here with all of you and saying that he's stupid and he thinks someone can't be 60 feet tall, okay? So is something possible to happen? Yes. Don't take one tail, take two tails. But in the question, if he says one tail, then match the alternate hypothesis that suggests only one tail, okay? I really needed to mention that, because I know that if he puts this trick, all of you will pick the alternate hypothesis that says this or that, but it's only one tail. Two tail is more like either yes or no, or one tail is only like, it's not like yes or no, because it's more like does it increase or decrease? But one tail is like, oh, it will only increase. How do you know? It could decrease. How can you make that judgment call? Because can you please give one more example? Okay, yeah. So the crash course. See, remember the crash course example? I should have not said that. I did that because I had to explain it on one tail for you to understand the concept. But on two tails, my alternate hypothesis, what it should have been correctly, is that the crash course could make you get better marks, or sorry, no, don't say good. The crash course will make you get better marks or worse marks. And it's true, it's possible. Maybe the crash course is wasting your time. No, it's not. I'm saying, come on, you get the idea. It's possible for this to happen. It's possible. Like, why should I only assume that the crash course makes your marks better? It's the same thing of when someone says, for example, like, let's say you have an exam tomorrow, like this. Look, my step 2 exam. Okay, it's coming soon. One day before my exam, I will not be studying. I will be relaxing, watching Netflix, maybe playing video games or something. So people will say, oh, you're playing video games for your exam. What are you doing? Like, that's obviously going. No, it's not obviously going to. What are you saying it's obviously going to? Relaxing before your exam might actually increase your mark. Why do you think it will decrease your mark? Why do you go through that, judgment call, right? Now, no one says that to me, but that's the thinking that I always feel. What will be the null hypothesis? That there is no change. The crash course does not change your mark compared to the population, right? So I really needed to spend some time on this because he loves questions like these. He loves them. He loves them because you really need to know what a hypothesis means. Doctor, are you saying, don't call me doctor? Alternate or alternate? Oh, sorry. Okay, so I say alternative. So I say alternate. So it's like, I don't say alternative because you can't say alternative. I mean, you could. I say alternate. So yeah. Oh yeah. Okay. So there we go. And if one more person calls me doctor, I'll not be giving ANOVA tomorrow. Okay, it's a joke, but anything's possible. So yeah. Let's keep going. So then they have no, it's fine. Don't say sorry. It's fine. Mean, standard deviation. They got all these data. Blah blah blah. We're not going to go over calculation. He just found them using Excel. Blah blah blah. We can find them through paper, but I mean, we're not going to do it. So then he gives you this. So then what did they find out? So let's actually. Oh, he didn't put the p-value here. Put the p-value here. Okay. So here, what happened is, I'm just going to go back to this. He's comparing drug A to 0 and drug B to 0. He's not comparing drug A to drug B. Very important to make that distinction. So here we have one statement on drug A and one statement on drug B. So let's start with drug A. The first thing we read is the first sentence. This is usually what's mentioned in, like, he does a really good job of writing this because this is what you read during articles. So drug A did not have a statistically significant effect. Okay. So already we should expect the p-value should be more than 5%. And if we go to p-value, right, it's going to be 0.2, which is 20%, it goes with our thinking. And if we go to the confidence interval, again, they're not mentioning population mean here because it's the null value, it's 0. So does this limit include 0? Yes, it includes 0, and that goes with the p-value to suggest to us that it's not significant, right? And this is another thing. It's not objective, but this is something I like to sometimes use. Like, the mean we're comparing is 0, and the mean effect here is 0.75. So the change is only 40 minutes or something during sleeping time. So that's nothing, right? Again, don't use the mean to determine significance because we use p-value for that. But sometimes I like to do this just to make sure, if I saw the mean effect, for example, 20 hours, and then I saw p-value is like not significant, my eyes would be open. I'd be like, how are they sleeping? 20 more hours, but the p-value is not significant. Like, I think there's something wrong. This is more of practical knowledge, not really like you probably made a mistake in calculation or something. But yeah, here everything is good. Everything, I like it. Okay, everything's good. Now let's go to drug B. Drug B had a statistically significant effect. Okay, so let's go to p-value. P-value is 0.005. It's less than 5%. So we all agree that it's significant, right? If anyone doesn't agree, just ask. It's fine. In this case, the confidence interval is 0.9 to 3.76. Does this include 0? No. So it goes with p-value, and we will think that it's significant. Now, another thing that I like to do is sometimes look at the mean. Oh, hey, look, it increases by 2 hours. That's actually pretty good. Like, imagine you sleep, for example, 6 hours. Taking drug B, you'll sleep for like 8 hours. That's pretty good. If someone is having trouble sleeping the full 8 hours, you could give him drug B. So that's how you read. These results. It's really important. It's really important you understand these results, what you look for, what you understand for, so on and so forth. I don't get how drug A, we said it's, no. I did not say drug A is significant. I said drug A is not significant. Yeah, so B is better than A. Yeah, so I'm saying B, the p-value was 0.2, which is 20%, which is more than 0.05, more than 5%. So it's not significant. And the confidence interval, it touches 0. So it's, again, not significant, right? We said if it doesn't touch 0, it's significant. So yeah. You should know how to do it. So B is better than A. That's the conclusion. Look, B looks as though it could be better than A. However, you need to remember something. We did not actually compare drug B to drug A. Okay, and now I'm going to blow some of your minds. Why do we have to know if 0 is included or not? Look, it's not that you have to know, it's just that if they didn't give the p-value, you can use the confidence interval. If they didn't give the confidence interval, you can use the p-value. But generally, they agree. You didn't get this slide? See, now, here is where I really need to kill someone. Because this slide, look, Bushra, remember the slide when we were talking about in confidence interval? When I tell you guys, oh, hey, this line, is it significant? You all say, yes, significant. This is the same exact thing. It's just instead of giving you the visual stuff, instead of giving you this stuff, they give you, first lecture. Get the cat away. Where is it? Dude, guys, relax. Just focus with this for a bit. This is the same exact thing. It's just with words, not with text. Basically, he will ask you. He will give you this sentence. He will give you this entire sentence. And then he will ask you, which of the following statements is true? And he'll write, for example, drug A is significant. Drug A is not significant. Drug A's effect size is more than 2 hours. Drug A's effect size is less than 2 hours. Like, he'll give you a lot of words and only one is correct. Yada, yada, blah, blah, blah. But basically, you have to read and understand this in order to be able to answer such questions. So it's the same thing. Look, Bushra, answer me this. If the p-value is greater than 5%, is it significant or not significant? Just write that, significant or not significant. P-value greater than 5%. Not significant. So it's the same exact thing here. Just when you see the sentence, go to the p-value. P-value. Okay, so here it's 0.2. That means 20%. Is 20% more than 5%? It is. That means it's not significant. So it goes with the text. It goes with the text. Your job is not just to read this. Your job is to go through also the numbers, okay? Now, let me erase all of this because I made such a mess. So, okay, you read this. It tells you it's not significant. How can we make sure? We look at the p-value. P-value is more than 5%. That means that it is also, it goes with what we read. It's not significant. How about we use another way? Confidence interval. Does this include 0? It does. Another way, it's not significant. Like the mean effect, it's very small. It's only 0.75 hours. Does almost nothing. The D and the T, forget about them. Okay, T is t-value. D is, we're not going to get into what D is. Okay, forget it. The things that you mainly use are mean, the p-value, and the confidence interval, right? If he gives you the p-value or the confidence interval, we always check if it includes 0 or that number can change. That number can change if he specifies it to you. He tells you the mean that we're working with, the population mean that we're working with. I usually don't know it, but he could mention it is 10. Then the confidence interval, you should start comparing it to 10, not to 0. Here, he didn't mention it, so by convention, it's 0. By convention, by tradition. Okay, so then let's read the next one. It said, here we assume the mean is always 0. Yeah, if you didn't mention it, the mean is always 0. So here, drug B had a statistically significant effect, increasing the duration of sleep. Let's make sure p-value is 0.005, which is 0.5%. Is it less than 5%? Yes, it is. That means it's significant. Okay, we made sure it's significant. Let's use the confidence interval, 0.9, 3.76. Does this include 0? No, it doesn't. Boom, significant. What about the mean? Look, it's 2.33 hours. It's actually very good. Okay, I like it. The effect size is good. Yada, 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 blah, blah, blah. You get it? So this is just a way to quickly, like you will read so much of this when you become a resident. You will, sometimes patients will come to you. They will tell you, doctor, I read this study. Could you please help me understand what it's trying to say? And then you have to go to the results section. You'll have all this text here. And now you understand how to read it, okay? We're not really saying anything new. Here we assume the mean is always 0. Yeah, it's always 0. Now, sometimes studies like to put in visual information, helps understand more. So in this case, we can make the same exact idea. Notice how this interval touches 0. But does this interval touch 0? No. No. Okay, I'm really happy all of you said no. Now, I'm going to give you, it's significant. So this would be called significant. Now, I'm going to give you guys a little tip. One of you mentioned something important that, okay, so drug A is better than, or drug B is better than drug A. I would agree with you. Yeah, it's better. Yeah. But is it statistically significant when compared to drug A? That we need to do another study for, because recall, here, we're not comparing drug A to drug B. We're comparing drug A to the population, drug B to the population, using the same set of patients. We're not getting more patients. But we're not actually comparing drug A to drug B. Now, later on in the results, it finds out you find out that it actually is like drug B is different from drug A, and you can even see it. Like, look, this confidence interval, does it touch this mean? No, right? No, it doesn't. That means that drug B, if you were to compare it, and we will compare it, to drug A, my cat is going crazy. If you compare drug B to drug A, you're going to find that it's actually significant. So drug B not only looks better than drug A, if you actually compare it, no. But Marwan, forget about what you just said. It's we can compare them with a dependent t-test. It's just in this example we didn't. We're comparing drug A to 0, drug B to 0. We didn't compare them together. Okay, so bring it back. Okay, so this idea, I want you to understand something. Didn't we say that drug A is not significant when compared to 0, and drug B is significant when compared to 0? What test we did? We did the dependent samples t-test, because the only thing that says it's dependent is that the same patient took the two different drugs. That's the definition of dependent. That's you're using the same patient and putting them into two different groups. He's the same patient, but he's both in drug A and drug B, but he's the same patient. Independent means that you have one person taking drug A, one person taking drug B. They're different people. Now, this is the idea that I want to tell you. Just because when you compare drug A to 0 and it's not significant, and then when you compare drug B and it is significant, it does not mean that just because you then compare drug B and drug A, that there will be significance. No, this is a wrong assumption. It could be significant, could not be significant. If you don't believe me, let me just make a quick adjustment to this curve. Let me pull this slightly out like this, and let me pull this slightly down more like this. Now look, this confidence interval includes this mean. This confidence interval includes this mean, right? Because it's here, includes this mean. So they're both, when you compare them to each other, it's not significant. But this drug, when compared to 0, is significant. This drug, when compared to 0, is not significant. So never do this rule where, oh, drug A was not significant, drug B was significant. So if I compare drug B and drug A, it will be significant. No, this rule does not apply at all. It could be significant, could not be significant. In this case, it was significant, but that's just, this case. Now, we did not finish the lecture. I don't want you all to celebrate. We actually have, this is the first part. We have just a few more things in the second part. Not ANOVA, right? This is nothing to do with ANOVA. This is to do with the second part of comparison of means. It's much shorter. Okay, and I love my cat. I don't want anyone to think that I hate my cat, but like, I'm trying to be professional for GNT. You should see how much I play with her like after I finish the crash quiz. Okay, so you all see this now, right? And I have the chat next to me. Okay, where is the pen? Okay. So this is all called related samples t-test. When you have one patient in both groups, like group A, like drug A and drug B, he's taking both medications. Now, this can be called paired samples t-test, correlated samples t-test, dependent samples t-test. This is all the same thing, all right? But usually the more common name is dependent. We use dependent and independent, but it could be any of the four names: related, paired, correlated, or dependent. Specific designs, for example, could be before and after. For example, before they take a treatment and after they take a treatment. This is actually the most common variation. They don't like doing drug A versus drug B. They usually like saying, hey, how are you feeling? Like, how is your pain today? You collect data. Then you give them the medication and you collect like after. And you say, how's your pain today? That will be an example of a dependent t-test. And that's how usually it's used. Rarely do you ever see drug A and drug B and people, because usually you can just get 16 and 16 on this side. You don't really get 16 taking the same medication. I'll explain why. It's to do with the fact that maybe, like, let's say I take drug A, I wait a week, then I take drug B. Using the half-life, maybe drug A is still in my system and it could affect the action of drug B. So it would not really be a true comparison of drug A and drug B. And this is called order effect. And we'll talk about order effect. Yeah, exactly. Exactly. Sometimes what they do, and we'll talk more about this, what they do is they counterbalance. They give 8 patients, for example, drug A, then drug B, and then another 8 patients, drug B and drug A. And although this is good, it's still not ideal. Okay, so just keep that in idea. Basically, wherever you find matched pairs, like for example, patient 1 taking both A and B, he's a matched pair. You give the name dependent t-test. Now, pairwise differences, basically, yeah, those matched pairs, you're just seeing the differences between those groups of data, between drug A and drug B, for example. And at each point, this data could be collected before and then after treatment, one treatment and another treatment, individuals matched. Yeah, this is another thing. This is kind of confusing, but basically, if you have identical twins, they don't consider it an independent samples t-test. They consider it a dependent samples t-test. If you have, for example, twin 1 taking A, and then twin 2 taking drug B, they technically consider this a dependent samples t-test, which is really confusing. I agree with you, but then just for the sake of the exam, just memorize this. And the reason they do this is because they have very similar traits, so it's unlikely that their differences cause the change between drug A and drug B. It's likely that the reason if there was any difference between drug A and drug B, it's likely because of the drugs, not because of them being different, because they're not different, they're identical twins. Now, remember when we compared drug A to 0 and then drug B to 0? What we can do is actually compare them to each other using the same dependent samples t-test. This is just another technique. What they do is they find the difference first. So you minus drug B from drug A, you minus drug B from drug A, and then you get all these differences, yada, 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 right? And you can notice also, he took the difference in terms of positive, right? Is there anyone that's negative? I mean, yeah, he took it in a positive sense. So, yeah, he took it in a positive sense. So, point is, like, like, it's just a coincidence that there's no difference that's negative, but there could have been a difference that's negative. It's nothing to do with like, it's not like these should always be positive numbers. There could have been a negative number, but in this case, they're all positive. So actually, we can do a one samples dependent t-test on these, but the interpretation is different. The interpretation is no longer to the population, but rather to each other. So let's go to the interpretation. Blah, 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 numbers, 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 numbers. This is really important. Notice that the t value is basically just the difference between the means. Here, move this because this is just 0, right? Convention just changes to 0. And then this is just standard deviation divided by radical. This is just SEM. This is just SEM. So SEM, T is the same as Z. The only difference is, Z and T are very, very similar. The only difference is not the calculation. The difference is the table. The calculation is the same. It's X bar minus mu, yada, yada, yada. We did all this and then divided by SEM, yada. So this and this are the same exact thing. So the calculation is the same. The difference is the table. The table is what gives you a different t value from a z value. So this is important because you'll see in a second there's a definition about t value, and it'll make sense when you see this formula. This formula. So now let's go to the results. So drug B induced statistically more sleep than drug A, and if you go to the curve, it kind of makes sense, right? So look, this does not touch this mean. You might be saying, no, it's touching 0. Forget 0. We don't care about 0. 0 here is not important because this 0 was for the population. Right now, we're caring about these two together. So this confidence interval is not touching this, and this confidence interval is not touching this. Yeah, here we're comparing drugs to each other. That's why in the results section, they mention drug B induced statistically more sleep than drug A. They're comparing the medications. So he could give you this results section. He can give you the results section, the two ones that we saw previously, one about drug A with the population, drug B with the population. He can give you all of that and then give you statements, and then you have to pick the right one. So this is important and how to read all of these. So let's read. They mention statistically more sleep. So where's the p-value? It's right here, 0.003. This is 0.3%. This is less than 5%. So yeah, we can agree it is statistically significant. In this case, this confidence interval, does it touch 0? I'm going to confuse all of you right now. I'm really sorry. But here, even though they mention that the mean is for drug A is 0.75, this confidence interval is related to 0, not to 0.75. So yeah, we still compare this one to 0. And there's a really long reason why. I'll tell you, it's because this confidence interval is not the same as this confidence interval. This is the general confidence interval, comparing it to 0. But if they were to be actually correct and give you all the data, they would give you this confidence interval exactly and this confidence interval exactly, which they didn't give you here. So this confidence interval is still compared to 0, right? It's still compared to 0. So does it touch 0? No, it doesn't. That means it also goes with what we think. It's 0. It's not significant. It is significant because it's not touching 0. But then you can even make sure of that by looking at the confidence interval. Does this confidence interval touch this mean? And does this confidence interval touch this mean? And they both don't touch each other's means, which is fine. Remember that this is not the same as this. All right? Can you repeat this part? Yeah, this is really important, okay? I don't know how to explain it. You just need to take my word for it, okay? So look. So each drug's mean is now 0. No. Look. Hamza, relax. Don't. Look, you guys are going to confuse yourselves if you ask questions. Look, here, this confidence interval is like 3.5 to 1.1, okay? This confidence interval is like 1.9 to negative 0.5. Do you see any of that information here? No, you don't see these confidence intervals here. For that reason, I'm telling you that this confidence interval, it doesn't have anything to do with this confidence interval and this confidence interval. This is a general confidence interval that they somehow calculated. I don't know how they calculated it, but the number they want you to compare to for this one is 0. I'm 100% sure of this. The confidence interval they want you to compare for this one is 0. This is the general confidence interval of this specific study. How they calculated it, how they got it, I don't know. But I am sure that they want to compare it to 0 because there's no way it compares with these. Okay? Now, you can see that the mean here is 0.75 and the mean here is 2.33, which if you go to this slide, 2.33 and 0.75. The means here are correct, but this confidence interval has nothing to do with these confidence intervals. This is a confidence interval of the study compared to 0. This 0 is basically, if it doesn't touch it, then we are sure that drug B is different from drug A, right? Is it to say that drug B is acutely significant? Is significant compared to? No. Look, it has nothing to do with 0. Look. I knew this would when I read this, I knew, like deep down, I knew it would confuse you. Look, when I say compared to 0, let's say it's not touching 0, then that means we are sure that drug B is statistically significant from drug A. I know it sounds really, really confusing, but just for this confidence interval, compare it to 0. If it's not touching 0, then we are 100%. We can say that drug B is statistically significant to drug A. Yeah, but yeah, we're using convention. But here 0 is not the population mean. It has nothing to do with the population. This is the confidence interval they made of the study, like as a whole. When you see the two different confidence interval of both drug B and drug A, it becomes a lot clearer. Notice how drug A is not touching this mean, and drug B, it comes all the way to here. It's not touching this mean, right? Did you also understand that? Which one's given first? Are we comparing 1 to 0 because it's given first? No. Look. Oh my God. Okay, just relax, everyone. Relax. Okay. So how do we decide the significance? Okay. Relax. No. Relax. Don't say sorry. Just relax. Everyone, stop asking questions. Stop asking questions. Okay? I will make it very clear. Okay? Look. First off, we can all agree that this confidence interval is up to somewhere like 3.2. And this one is like 1.1. So the first drug B confidence interval is 3.2. And it goes to 1.1. The second confidence interval is like 1.8 all the way to negative 0.5. Now I want to ask you something. Do you see any of those numbers in this confidence interval? No, you don't see anything. So this confidence interval, I can assure you, It has nothing to do with when comparing these means. Do not make the mistake of saying, oh, hey, look, this confidence interval includes this mean. That means that it's wrong. And this confidence interval also includes this mean. That means there's no significance. Why are they saying there is significance? No, no, no. This confidence interval, compare it to 0. How they found this confidence interval out? No idea. I think they used Jamovi or Excel sheet or whatever. Point is, this confidence interval is being compared to 0, but not 0 population 0. 0 in terms of if it's not touching 0, then khalas, drug B is significant, and it's when compared to drug A. That's the 0 that they're talking about, not the 0. And again, how did they find it out? Usually the 0 should be the population one, but how did they find this one out? I have no idea. But that's what they're trying to say. By the way, is this t dependent? Yes, it is t dependent. So if we go here, we can, add more onto it. If we use the confidence interval here and the confidence interval here, we have the exact numbers. Then I can compare this confidence interval to this mean. So is 0.75 in this confidence interval? No, so it's significant. So we're sure that drug B is statistically significant when compared to drug A. And this one is 2.33, the mean that we found here, 2.33, the mean that is also here. Is it included within the interval? No, so we also can say that drug A is statistically significant when compared to drug B. Okay, just one thing, because someone said, can we just use the p-value? Yes, you can, but what if he doesn't give you the p-value? Khalas, you get the question wrong? No, you should know confidence intervals. And I admit this confidence interval is very confusing, and there is definitely a way they calculated it, but the comparison point is 0, not these points. Why? I don't know. I don't know why they chose to do this. I wish he just mentioned the confidence interval for drug B and the confidence interval for drug A, and then showed you this slide instead. Instead, he puts this line in here. But I assure you, you compare it to 0. Okay? Yeah, so both are statistically significant on slide 6. Yeah. Okay? And that goes with everything that's happening here. The p-value, the text, the p-value, and the confidence interval that's compared to 0, and the means and the graph, everything here, all of that is sort of understood, and you should have like understood it from this example. And we had 0, yeah. So this is a good question for Huda. If in this exact example, let's say we compared it to 0 and 0 is included, then that means that this statement is wrong. It means that drug B and drug A are not statistically significant, meaning that they're sort of similar. Drugs are not significant. Okay. Irtaza, in this example, I think your question kind of confused everyone. If the confidence interval here was including 0, then this p-value will be more than 5%, and they will write here not statistically more than drug A, blah, 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 blah. And here, this will go further to the mean, and both will be including the mean. But now we're living in a world and a slide which says the exact opposite, which says that it is statistically significant, where the confidence interval does not include 0. Therefore, it is statistically significant when you compare drug B and drug A to each other. And the p-value is less than 5%, which means, again, goes with everything that we've been saying, confidence interval, it's statistically significant. And if we go to this graph, this further elaborates everything that we've been talking about. This confidence interval does not touch this mean, and this confidence interval does not touch this mean, further elaborating the fact that it is significant. Now, I know what you're all thinking. Oh, I'm just going to use the p-value. What if he just gives you this and tells you interpret it? Because in step 1 and step 2, they do give you this, and they do just tell you ask it. Even I think in SMLE, I think they do ask this stuff. So the Saudi, if you want to do the Saudi board, they will show you this, and they'll ask you interpret it. Like they'll show you 5 different answer choices, and only one will be correct. And you're not going to know how to answer unless you know how to interpret confidence intervals. So, yeah. Does everyone understand this? I only care if I see one no, so let's take another swig of coffee. All right, so you're all good. All right, so now we're talking about two independent sample t-tests. You all understand how to read and everything. Again, I really think you should just ask him if you should know how they got these numbers. I don't think they really care. Okay, now it's a similar procedure to one sample t-test or the dependent sample t-test or the related sample t-test, but the only difference is that instead of using the same person to be in the two different groups, the drug A and drug B, no, we are actually putting two separate individuals, one person taking drug A, one person taking drug B. Okay? And then they mentioned this thing down here, which should have been mentioned in the beginning, that the t-value is the number of times the standard error divides the difference between two means. And that's exactly, this is the definition of the formula. Right, let me clear all of this so I can show you it. It's the standard error divided that many times into the difference between the two means. All right. So again, we all understand this, we all know this. So here he gives you the same example, but instead of having one group, for example, one group having their phones taped to their heads, remember the previous example, and then comparing that to the population, no, here he has two groups. One, both of them have their phone on their head, but one is the phone is turned off, the other the phone is turned on. So now what they do is they, just the same exact thing. Null hypothesis is that both groups will be equal. The alternate hypothesis says that no, the phones will have an effect, either positively or negatively. Either they'll make them smarter or they'll get worse marks. So they don't give you the results here, which is fine because I really don't feel like going through them. But there are some considerations when we talk about the independent sample t-test. We have two estimates for the variance used to calculate SE. So what this means is that, these 16 people and these 16 people, how do I mention this? Like, didn't we say that they are different people? So the variance with this group might be different than the variance with this group. And that's important because when you were doing this, a one sample t-test, there's no variance. Look, this is another trick, another terrible trick. And we didn't have it as a question, but I was expecting this to be a question. Basically, he says that a one sample t-test has low or variability. That is a false statement. A one sample t-test has no variability, right? Or there's no variability between the groups. That's how I should have said it. There's no variability between the groups. And the reason is because it's literally the same person taking the drug. So how can you say the one group is different from the other? It's literally the same 16 people in both groups. So here it's different. In the independent, it's different. You have 16 people here and 60 people here. So there's an important consideration. Maybe these people in one group are more related to each other than the experimental group, right? Like maybe these people. So yeah, okay, for Sarah, this is just for everyone to commit to memory. In a dependent samples t-test, the variability, it's not there. Just memorize it like that. In an independent samples t-test, it is possible for it to be, like the cat made me lose my train of thought. In an independent samples t-test, it is possible for there to be a difference in variance when comparing one group to another. Okay? And don't, yes. Look, I will let the cat enter the shot, but please no one talk about the cat because I want you focusing on this idea. Okay. The little camera shy. Okay, so the variability is the same independent samples t-test. In independence, the variability can differ, and that's an important consideration. Okay, so that's exactly what they're saying here. For these reasons, we adopt a conservative approach and use a t-test which assumes the variances are different. Now, you can do another t-test which assumes that the variances between the groups are equal, but generally you don't use that one. It's very rarely you use that one. Generally, when you do an independent samples t-test, you use the one where there is heterogeneity of the variances, because by convention, if you by thinking about it, by logic, by simple logic, if you have random groups, like there's random people in this group, random people in this group, the variances are likely not going to be the same, right? And this is, I feel like this is something that should really come to you in terms of an obvious way. So like, do you all understand this? We could try to make it close. Yes. So Iman, you're right. You could try to make it close, and in that case, where you try to employ techniques that it becomes equal, similar to each other, then you can do something called a t-test with homogeneity of variances. That's where you do the t-test and you specifically ensure that the variance in one group is equal to the variance in the other. But that requires more technique, more skill, and is generally harder to do. So by convention, the standard is to use a t-test with heterogeneity of variances, because you can't guarantee that the variance of one group will equal the variance of the other group, since there are different people in this group than to this group. That's the simple idea. This makes little difference if the two sample sizes have equal variance, but it can help, using the heterogeneity of variances way, it can help if they are unequal, which makes sense. They give you the data, blah, blah, blah. They give you the result. They found out that it's not significant. And if you look at the p-value, it's slightly more than 5%. That means, using phones that are on makes no difference from those that don't use their phone on, same idea. Okay, now I'm going to give you a little, we're not going to do this. Okay, we're not going to do this. This is way too late for us to do this. Okay. Assumptions for all t-tests, okay? So the assumption here is that it always has to be random, unless if your specific design requires you to not be random for a specific point. What do I mean by that? Maybe one group has to be, for example, all smokers, and the other group has to be all non-smokers. Maybe it has to be like that. In that case, it can still be a t-test, right? And that's called quasi-experimental. Yeah, so this is it. So participants must be randomly divided into two groups, and it's fine if it can be a quasi-experimental, okay? So if you, for example, separate them based on men and women or this, it's fine. It's not the worst case scenario, but ideally it should be completely random, right? And now what are the assumptions? I skipped over this slide. Yeah, we went to here. We skipped over this slide. The assumption for all t-tests, that the observation are random from a random sample, that participants are independent of each other. This is obviously, like, it has to be like that. What they mean by this is not independent sample t-test. What they mean by this is participant 1 is different from participant 2, different from participant 3 and 4 within the same group. You get it? So point number 2, like let's get a dependent sample t-test. If we have a dependent sample t-test, we have 16 people that will take first drug A, then drug B. Person 1 is independent of person 2. Person 2 is independent of person 3, so on and so forth. Yeah, quasi-experimental means dividing based on a specific factor, like, for example, smoker, non-smoker, married, divorced, or, for example, what else? Like, yeah, like, you get it. So now, another thing is that usually it has to be normally distributed. Now, it's fine if it's not just normal distributed, but only if the sample mean is, or the sample, size is more than 15. It's fine. If it's less than 15, you really got to ensure that it's normal. And how you do that is using sampling distribution, yada, yada, yada. We talked about these techniques earlier. So yeah, we talked about all this. We talked about this. Now it comes to compare the two together. So what's the difference, or what are the advantages between an independent versus a dependent? And in this case, they're doing the opposite. What are the advantages of a dependent one versus independent? All right, so one is you avoid the problems of variability. That's a really big one, because you essentially completely destroy the variability between the two groups, because it's the same person that took drug A is the same person that took drug B. There's no variability between those two people because it's the same person. So variability is I don't want to say minimized, it's completely removed, okay? Of course, the variability from person 1 to person 2 exists, but the variability from one group to another is non-existent because it's the same person. Okay, do you mean between groups or within groups? Now, this is more into ANOVA. I don't mean between groups for ANOVA. That's a separate between groups variance. That's a separate, oh my God. Allah, I hate your question so much. There is something when we go to the ANOVA lecture called between group variance. Now, sometimes even if you use the same people, you get a different between the group variance. That's not what I'm talking about here when I say there's no variability. What I'm saying here is that since the same person who's taking drug A and drug B is the same person, you really don't have to worry about that person being a different person. You don't have to worry about the variability. You don't have to worry about, hey, maybe the person in drug A is a smoker and the person in drug B is a non-smoker. Maybe that's why drug A and drug B are different. You don't have to go through those problems. And that's why I say the variability is non-existent. I am not saying that the between the group variance is minimal. I'm not saying that because that's a different term. What I am saying is just that since this person is the same as the person taking drug B, this worry that, oh, maybe he's a smoker and he's a non-smoker, maybe he's elderly and he's not elderly, maybe he has high lymphoma and he doesn't have lymphoma, you don't have to worry about any of that stuff. It's the same person, same person. The group that's given drug A is the same group that's given drug B when it's dependent. Yeah, and that's why we say it avoids any problems of variability, right? It's a variability essentially here is non-existent because it's the same person. Participant variables confounds have little effect. This is exactly the same point as one, but they bring this term called confounds. Basically, you don't have to worry that it's the same idea that you don't have to worry that it's the smoking that's caused. Maybe him being a smoker caused the drug to work, or maybe him being because believe it or not, being elderly, just being elderly, could possibly make a drug work or not. And you will learn that when you study STEP. There's something called being a slow acetylator and someone being called a fast acetylator. And these are two different populations, usually elderly versus young. Young are fast acetylators, elderly are slow acetylators. So what's the point of this? It's that, being elderly alone might actually decrease your metabolism of the drug and cause you to have more drug in your system. So maybe the difference between age is causing the difference between drug A and B, not the difference between, not the actual difference of the drug. You essentially remove this variable by using a dependent sample t-test. Because if he's an elderly taking drug A, he's still an elderly taking drug B with a dependent sample t-test, right? This is the same point as avoiding variability. It's just said in a more fancy way. Fewer participants, I feel like this is obvious. Instead of getting 32 people, you have 16 people, right? You get fewer participants. What are the disadvantages? One is order effects, which is really important. So, for example, fatigue, carryover effects, drug persistence. Let's say, for example, like I'll give you an example of fatigue. You ask someone to run a marathon taking drug A. Then in like 2 days, you tell him to do the same marathon, but taking drug B. He's going to be really tired after the first marathon. So the second marathon, you might get a lower result or an unexpected results, but not because of the drug, because he's fatigued. So these are called order effects, where the order of where it happens is accounting for the difference between the drugs, not really the drugs themselves. It could be fatigue, could be drug persistence, carryover effects. These are all the same thing when it comes to drug A versus drug B, right? In some studies, participants are more likely to guess the purpose of the study. I love this because you'll again sometimes get this question in your board exams, and this is called the Hawthorne effect. And I'll give you a really quick way of understanding this. Let's say they do a study, okay, at Faisal University, where they hide. They'll tell you, well, we're gonna hide microphones in all the PBL rooms or the library. At every table there is a microphone. And they first collected data without telling us, right? And then they collected data after telling us. So no one's gonna, could someone like stop recording? Could you guys stop recording? I still see the recording sign going on. So let's say, for example, someone, I stopped the recording just because of a sensitive thing. Well, point is, basically, let's say there was a study where you were giving patients with osteoporosis certain exercises. It's hard to give an example on this. Like sometimes they okay. How about this? How about this? This is a good one. let's say an anti-vaxxer wanted to come to your clinic and he wanted to participate in your study about vaccines. So you're going to test, for example, COVID-19, the COVID-19 vaccine. So then he looks at you and then says, oh, hey, why are you testing the COVID-19 vaccine? I'm going to have to really edit this one because I'm not going to be making fun of anti-vaxxers during the YouTube video. Point is, he might know that your study is trying to prove that the COVID vaccine is good. So he might intentionally fake a rash or something, or like, intentionally make a fever or something, just so that you don't end up finding significance with the vaccine, right? So this is an example of where the study might fail because the person knows what you're doing. Like, for example, let's say you give him vaccine 1 and then vaccine 2. He'll maybe understand that, hey, I need to act good for vaccine 1 and then batch of vaccine. It's really difficult to sort of give you an idea about this. What is this effect called? Yeah. So this effect, it's a specific effect where people change their behavior because they know that they're being, recorded or monitored or being collected in terms of data on them or something. This effect is called Hawthorne. It's H. Oh, I'm gonna spell it out. Hawthorne, and then it's like ORNE. This is called the Hawthorne effect. When people change their behavior because they realize that, hey, he's collecting my data and stuff, I can now pretty much change the result of the study just by doing something different, right? So, like, these people that were doing the test, maybe they were like, oh, we don't want to put the phone on our head, so I'm going to intentionally get a bad mark because I don't want them finding significance, right? So this is an example of people doing that. But he wouldn't know if you're doing if you do the test twice, he'll obviously know. He'll do well the first time, then bad the second time. Or maybe he'll do well the first time, then even better the second time. It's up to him because he understands that, oh, he's doing this test twice on me. I have to change it this time around, I don't know, people are bad like that. But you have to understand that it is possible for people to do that sort of thing, right? The last one is that, unfortunately, if, let's say, participant 1 that we did drug A on and drug B on, let's say he left the study before we could do drug B, then we also have to get rid of drug A, right? Because it doesn't make sense to include drug B but not include drug A. This, in an independent sample t-test, is fine. If your participant 1 in that group left, it's fine. You can keep that. You can keep the other one in drug B. It's fine. But when it's the dependent sample t-test, where the same person is taking drug A and drug B, only takes drug A and ditches your study, you can't use that study anymore. You can't use that participant anymore in your study. Last but not least, our final slide dictates how we can reduce this, how we can reduce order effects. So how do we do that? It's very simple. We have a number of ways. The first one is counterbalancing. I already talked about it earlier. So you give, for example, you have 16 people. You give 8 people drug A, then drug B, and then you give the rest of the people, the other 8 people, you give them drug B, then drug A. This is called counterbalancing. You can counterbalance, but randomize it. So, for example, you flip a coin, and then if it's heads, okay, you get A then B. If it's tails, okay, you get B and A. It's the same as counterbalancing, but instead of actually dictating people, do independent sample. What do you mean, do independent sample? Oh, yeah, no, I get you, yeah. The last one, guess what? It's very obvious. You do an independent sample t-test. That's how you reduce order effects completely. So use matched pairs or independent samples design, right? So matched pairs in this case is like twins, right? So twins can't have, twins are considered, dependent sample t-test. So if you use twins, they're not going to have order effects because they're two separate people. And even though they're two separate people, it's still considered dependent sample t-test. The other one is delay. So for example, you give him drug A, then you wait a month, then you give him drug B. This also reduces order effects. So yeah, with that, do you guys have any questions on this? Can you please repeat counterbalance? Yeah. So counterbalancing means that if you have 16 patients, you give 8 of them drug A, then drug B. Then the other 8, you give them drug B, then drug A. Right? So you're counterbalancing because the effects in the first 8 where A affected B, it'll be the opposite, theoretically, with drug B to drug A. Now, this is not ideal, but this is it would reduce the order effects for that study, right? Right, cool. Okay, if we had to calculate t-test, it's the same for all to the t-test. If you had to calculate a t-value, yeah, it's the same. It's just the means minus the mean divided by SEM. But the entire idea is that the t table is different from the z table. I doubt he'll ask you how to calculate t, but it's fine. All right, I'll talk. Wait. Randomization of treatment, please. Okay, I'll repeat it. Randomization is the same as counterbalancing, but instead of actually picking people, assigning them, who will take drug A or drug B, you randomize it. So, for example, participant 1 will flip a coin. Okay, heads, you now are taking drug A then drug B. Participant 2, flip a coin. Okay, heads again, you're going to also take drug A then drug B. Okay, participant 3, flip a coin. Okay, this is tails. Now you are going to take drug B then drug A. So it's the same as counterbalancing, but instead of dictating who will get what, you randomize it. And this should do the same thing as counterbalancing. What is slide 10? Let me go to slide 10. This is slide 10. Yeah, so this makes little difference if the sample size is differences. Okay, so usually with an independent samples t-test, you don't have, like, it's not going to work out like in this example. It worked out perfectly, and we have 16 and 16. Where's the example? Where is the example? Was it before? Yeah. So this example, it worked out perfectly. It was 16 and 16. Now, as that sample size, as it differs between group to group, generally the variance also can, it's not necessary for it to change, but it could generally be different from one group to the other. So, you know, if you have two groups, and for example, you know that the sample sizes are not the same, then you will analyze it using the heterogeneity of variances. And by doing this analysis, maybe their variances from this group and this group are equal. Maybe they are. So it won't make that much of a difference if they were equal, but it will make, you know, a huge difference if they weren't equal. If they weren't equal, this heterogeneity of variances will help you in finding the correct result. Okay? And I think the only way you guys can really understand this is by going to an Excel sheet, and I show you this. So let me just quickly, instead of sharing the Excel sheet, let me share my screen. Okay, so I was actually fidgeting with some of the examples to see how he calculated it, just to be sure. I cannot open sheet 3 for some reason. There we go. So if you actually go here and press equal t, and this t-test, what you can do is you can click it, and then you can put in your first set of data, then your second, and comma, then your second set of data, and then you do comma, and then you do two-tailed distribution, because we always do two-tailed distribution. And then here's your choice. You have paired, which is, you know, dependent samples t-test, and you'll have, this will be drug A, drug B, so on and so forth. Or you can have two sample, but either equal variance or unequal variance. Now, if you are sure that, and you use techniques to make the variances equal, you can use this one, right? And this is called, you know, statistic, whatever. We don't care. It's called, another name for it is homogeneity of variances. But this, if you use this and the variances are not equal, you're going to cause a huge problem. The result you get is not going to be the true result. So for that reason, they say always use this one, because the variances are most likely not going to be the same, because usually you're not going to have the sample size the same. If you can't even get the sample size similar, you expect the variance to be similar, it's not going to be similar. So for that reason, they say use this, because, you know, if the variances happen to be similar, all right, it won't cause a problem. But if the variances weren't similar, this will give you the correct result. Not like this one. This one will not give you the correct result. This one will give you the correct result. So I don't know. You all see what I'm saying here, right? How do I stop sharing screen? There we go. Can you please re-explain how to interpret the confidence interval of drug A and drug B? Of course. I still have it up. Thank God for that. Do I still have it up? I don't think I do. Oh, no, I do still have it up. Okay, so we can go to Zoom and then share screen, and then we can go to PowerPoint. So the time right now is 9:40. We can actually finish ANOVA if you guys want to finish it now. I know it's kind of getting, it's actually not getting late. Okay, so let's go back to the, where was it? This one. So let me erase the ink. So look, here he's giving you the confidence interval for each drug. So this is a lot easier to look at it. So remember when I was telling you that if this confidence interval does not touch the mean, is this considered significant or not significant? I want Irtaza I'm sorry if I'm getting your name wrong. Significant, exactly. So here's the exact same thing. The only difference is that here's the interval, and you compare it to this mean. So is it touching? No, it's not touching, so it's significant. Same thing can go for this one. And oh, you know what? Actually, you reminded me of something. So is this significant? It's not significant, you know? And you know, this is generally a rule. If the first one was not significant, the second one was, sorry, no, it is significant, it is significant. If the first one was significant, the other one has to be significant as well, right? It can't be that when you look at this confidence interval, this is significant to this, but when you look the opposite way around, it's not significant. There's no way that will happen. If that one is significant, the other also has to be significant. There's another thing that I do not understand in this. I think it's the problem with Jamovi. I think Jamovi does not draw perfect figures. So please, before we close this lecture, I want you all to go to Dr. Peter, and I want you to ask him, if this is not statistically significant, why is this mean not being touched by this confidence interval? I do not know the answer to this. So if someone could please ask the doctor this, I would be very happy. Now, my idea is that this curve is not that well drawn, this diagram. Jamovi, I think maybe he made a mistake and he accidentally, like he showed you here, back here, how he got everything. I think maybe there's a mistake in the calculation or something, or perhaps that the actual Jamovi is just absolutely terrible when it comes to making very detailed drawings, right? So I don't know why this is not significant, but the confidence intervals suggest that it is significant. Even if you look at the p-value, it's not significant, but the confidence intervals here suggest that it is significant. So I really suggest you ask him this. I really, really suggest you ask him this, because I don't know the answer. And my best guess is that this graph is not that well drawn, right, by Jamovi itself. So yeah, we finished this lecture. Do you guys have any questions? Okay, now we have two options, okay? I'm really